Hey, Science 30s, and welcome to the final unit of the course. We're going to be discussing energy and the environment for Unit D. We're going to be starting off with the first chapter of the unit, which is entitled Dreams of Limitless Energy, and that's going to be found in your textbook on pages 468 to 521. Your data booklet pages that you're going to be wanting to access for this particular chapter, you're going to be wanting to look at pages 1 and pages 3 to 8 are all going to be applicable pages in the data booklet for you as we move forward. So for today, I want to start off with topic 1.1, which is energy on demand. And we are a energy loving society. We be, and we're always looking for more and more energy, it seems, to power our daily lives and everything that we do in our homes and our businesses and our industries here in Canada and in a lot of other countries in the first world, countries all around the world for that matter. But it's always a matter of how can we meet these demands that are constantly seeming to be increasing. But I guess before we start the discussion about energy demands, maybe we should look really quickly at what in fact energy is. What's the physical definition of energy? Again, you've heard it before probably if you've been in any science classes or you've been awake over the last several years. But energy, technically speaking, is the capacity to do work. Now, what does that mean? That's kind of maybe a vague definition. Before I move on, you may want to take a peek at this quick video that's going to give you a really good explanation as to sort of what the heck that actually means. Kind of puts it in more quantitative perspective for you. So give that video a watch if you're just still a little bit vague as to what energy is or what's it all about, because energy is sort of at the heart of what this unit is all encompassing for sure. So to start off with global consumption of energy, and I don't think this is a surprise to anybody who's in this course or anybody who's living out their lives on a daily basis here in Canada or North America. Energy demands have been exponentially increasing over the last several decades, and this can't be sustainable. It simply can't. We can't. There's simply not enough ways for us to produce energy without basically taking this planet apart in the process, trying to fulfill these energy needs. To give you a couple of, I guess, numbers to throw at you, just to kind of put it in perspective for you, what does that mean? Well, the world uses, in 1 year, it's estimated that the world uses roughly 500 million terajoules, TJs, okay, terajoules. That corresponds to the release of, that's equivalent to if we released a Hiroshima nuclear bomb every 4 seconds throughout the course of the year. That's how much energy is being used by the planet just to power everything that we as a human society do. Quite a bit. And again, not sustainable if these energy demands continue to increase. 80%, about 81% of the energy requirements that we get are from fossil fuels. That's a problem. And we know the link between fossil fuels and global warming. This is part of the problem. It isn't just industries using the fossil fuels, and for us, I mean, we're using these fossil fuels as an energy source, vehicles, homes, the like. It's a major problem. We have to maybe find other ways that we can actually create energy, and that's what this unit is going to be discussing: different methods of energy creation that may be more eco-friendly, more environmentally friendly for the planet. Our use of energy is expected to grow at current rates about 35% by 2035. So between about 2010 and 2035, they're expecting to go up by about 1/3. So that's, again, a substantial increase. Again, how much more can we actually increase this until we sort of hit a tipping point, right? And the use of renewable energies, which is sort of what the heart of this unit's about, things like hydropower, using biomass, solar, geothermal, tidal power. That's expected to grow roughly only 4% in the same time frame. So we're going up by about 35% energy consumption. We're only going up by about 4% with renewables. So again, roughly 30 or so percent of that increase is going to have to be lifted by presumably burning of more fossil fuels, which again is going to exacerbate the problems with, you know, acid deposition, which we talked about. Well, burning coal produces, sulfur dioxide, which can then be released into the atmosphere to create sulfurous acid and sulfuric acid, or it can just lead to things like, global warming and acidification of the oceans. So this is something that really needs to be addressed. And how can we increase the demand for energy use, or can we maybe be more efficient in our use of energy? And Canada overall hasn't been the most efficient energy consumer on the planet. We are probably per person, we're one of the worst energy users in the world. Right now, our per capita use of energy is roughly 5 times the world average. So per person, we're using about 5 times the amount of energy that any other country in the world is using. Our per capita emissions of greenhouse gases are about 3.2 times the world average as well. That's double that of China, but we will get back to sort of why we're not maybe as big of offenders. It's a stat that, all said and done, we still do not produce the amount of greenhouse gases that China does, and there's a simple reason for that, and that's population, which I'll get to here in a little bit. Hydropower makes up about 59% of all the electrical generation in the country. That's a good thing because that's a renewable form of electrical generation. It's mainly in Quebec and down east. They're using a lot of hydro. BC uses a lot of hydro. Alberta, not so much. We'll get to what Alberta does here in a couple seconds. Alberta ranks below the world average of about 3.8 of non-hydro renewable energy. So, which is we're at about 3.1. So we're just below the world average with using other forms of renewable generations of electrical energy, like biomass, solar, tidal power. So there is some work to be done there as well. And this is well below the U.S. Believe it or not, the U.S. has got more renewable energy percentage than we do. They're about 5.3, and Denmark kind of leading the pack there. Denmark's at about 25% of their electrical generation is through renewable energy creation that isn't hydro power in origin. Canada doesn't have a sustainable energy strategy, but based on the evidence, it should largely focus on reducing energy consumption across the board in industry, housing, and transportation. That is something that we need to look at to be more efficient per person with our use of energy. A great deal of the energy in Canada is used to support the quality of life that extends well beyond our basic needs. We are very much a consumer society here in Alberta and in Canada. For example, since the 1990s, there's been a shift away from cars to SUVs. Maybe that trend is beginning to take a bit of a turn, but where people are taking big vehicles that consume more gas, per person. They're not as energy efficient, these vehicles. This is basically increased average fuel consumption per person in the country. Roughly per year, the average person is spending roughly $370 on just fueling their vehicles, which seems low, but you got to remember there's a lot of people in this country that don't drive, that aren't able to drive, or just don't drive. So this is spread out over the entire population of the country. So obviously that figure would be considerably higher, considering that you tank up your tank of gas and you're paying $40-50 per tank. This is obviously an average for every person that lives in the country. And there's some other people that don't necessarily drive to work. There's people that commute to work. But again, it's an overall average, this 370. Canada has what we call a high energy intensity economy. Our gross domestic product, which is the amount of goods that we produce in a year, is roughly $1.8 trillion. That's what we produce annually in the country. And basically that's the total amount of our goods that are produced every year. If you take that gross domestic product and divide it into the actual amount of energy that's used, dollar per dollar, we are among one of the highest energy users in the world. And again, part of the reason is our country has a lot of exporting of finished goods as the basis for our economy. We're also doing a lot of oil extraction, which also can be very high intensity in production of or use of energy in order to get these fossil fuels out of the ground or out of the oceans. So for that reason, because of the way our economy is sort of what we're basing our economy on, is very energy intensive. So that's a worrisome because how do you reduce the amount of energy if your economy is needing a lot of energy to basically make money to keep the country going? If you compare our energy intensity of our economy to other countries in the world, um, we even though we're working to a more efficient economy that's going to use less energy, we still are ranked. This was in a study in 2000. This is about a little over 10 years ago. We were ranked 17th out of 17 peer countries. We were like basically bottom of the pack, and that had actually that we were still at the bottom of the pack, even though we had reduced our energy consumption by 40% since 1971. So even though we are striving to reduce the amount of energy we're using, we're still well above where a lot of other countries are, dollar per dollar, to make the money that's coming out of our economy. So this is something that we need to work on. If you compare us to even all the countries in the world, and this was as of 2011, these were 2011 stats for GDP, Canada was the third highest energy intensity economy in the world. We were only beat out. Not that that's not something we should be proud of. We only got beat up by two countries. A lot of countries had lower numbers than we did. We should have much lower numbers. The two countries that had higher energy intensities than we did, Russia was just ahead of us, and Iceland. Iceland was very high, and the part of that is because Iceland has a very small GDP, and they do have a lot of energy use to get that GDP. So it's sort of a skewed number because Iceland is such a small populated country, and you could argue that Canada is the same way because technically speaking, we do have a fairly small economy, or sorry, a very small population compared to other major countries around the world. That is part of the reason why we also have these the high per capita energy use, which I'll get to here in a couple of seconds. In fact, I'll get to it right now. Our per capita use of energy is very high. And again, that's because we're an industrialized country, low numbers. We don't even have 40 million people living in the country. So that can be misleading because we have a very small population. When you compare us to, say, a country like China, even though we're much higher per person than China. Well, China, and if you look at another country like India, the two highest populated countries in the world, those two countries combined have 2.7 billion, not million, 2.7 billion people that live in those countries. So even if they've got lower, per capita energy consumption, they still have to produce energy for all these people to have, either vehicles or homes to heat their homes, to produce the food to feed all these people. So that is something you have to consider as well. It isn't just always about the per capita energy consumption, even though that is a worrisome stat for Canada. We don't produce overall compared to some of the other bigger countries in the world, population-wise. We are still producing, smaller amounts of energy because we're dealing with much larger economies in countries like India, China, even the U.S., Brazil, Russia, these much more heavily populated countries. So to put that in perspective, just to give you the numbers, China and India being at 2.7 billion people, that's 75 times higher than the entire population of Canada combined. So that'd be like having 75 Canadas basically pumping out their energy. And even if they were half the per capita energy intensity of Canada, which in some cases they are, you're still looking at 75 Canadas as opposed to only one Canada that's maybe twice as its energy use is twice the amount per person. That's only one. There's only one Canada. China and India, much larger populations that are going to give you much bigger things. Here are the stats for per capita. The per capita Canada, according to this 2014 study, ranked eighth per capita in the world. It was beat out by, again, a lot of other smaller countries that had smaller populations, but just huger, I guess very large amounts of energy consumption based on their small populations. We're dealing with the United Arab Emirates ahead of us, Luxembourg, Brunei, Kuwait, Trinidad, Qatar, Iceland. These are all small countries that are all, in many ways, has, a lot of energy use despite their small size. So that's the reason why their numbers are much more spiked. Major factors that affect the overall energy output or the energy use, I should say, of a country. There's three big factors at play, in which I've already sort of alluded to already. You've got population, climate, and activity. Population is huge. You're dealing with a lot of third world countries right now that are trying to catch up to the Western world, to the more industrialized countries. A lot of them have much larger populations, so this is going to be a bigger issue moving forward, as a lot of these countries that are trying to kind of get a piece of the industrial pie, as it were, but with much larger populations, their energy could be spiking, and this is where we're going to maybe see that 30 to 35% energy increase over the next several years. We also have climate. Excessively hot or cold countries tend to use more energy to either heat their homes or cool their homes. Canada being one of these countries that's up in the north, we have to heat our homes for long periods of the year. I mean, our heaters are on almost 9 months of the year sometimes, depending on how cool and the springs are and how early the cold fall comes in, or the winter comes in at the end of the summer there. This is an issue, and that's partly why Canada has this higher per capita energy use, because we are in a cold climate, right? And again, think about the stats I gave you earlier for energy intensity. Where were those three countries that have the highest energy intensity? Iceland, Russia, and Canada, all very northern countries. This also plays a role with the energy use of these countries. Activity is also going to play a role in the overall consumption of the energy consumption of a country. How much work is being done in a country will determine the amount of energy usage. For example, more activity in the transportation sector will require more energy to move those vehicles around. So depending on what the economy is based on of the country, what type of economic activity is going to be there, that's going to also determine the amount of energy that's being used. Some economies are going to use less energy just based on what they're producing or what they're actually exporting, compared to other countries like ourselves that produce a lot of finished goods and a lot of fossil fuel extraction that is generally considered to be more energy intensive. Human energy use has not just increased; it has continued to grow at exponential rates. If you want to take a look at the history behind human energy use, take a watch of that video. Great look at the historical context. I mean, we're talking like long historical context of human energy use over the years, and just to see kind of where it's been and where it's going. Kind of an interesting look at it from a historical standpoint. The global need for energy is not going to reduce. This is something I think that pretty much everyone's going to understand, that populations around the world are increasing. We need more and more goods to give people around the world. We understand this. So we got to make our use of energy more efficient. That's really what it boils down to. We're not going to reduce economies to basically stop using energy, but can we be smarter about the way we use our energy? And yes, we can. And when it comes to efficiency, there is a way you can calculate efficiency, and that's sort of the math part of today's lesson. It's how do you calculate efficiency? What is efficiency? Well, efficiency essentially is how much useful energy am I going to get out of a system compared to the amount of energy I had to put into the system, right? So and again, let's say I'm using like the units like joules. I'll use joules as my units. Let's say I had 20 joules I had of output energy, and let's say I created a toy car that had 20 joules of output energy, and it was able to move the car. But in order to make that car have that 20 joules of energy, output energy, to make it move, I required 100 joules of battery power to basically make it move. Well, what's the efficiency of that vehicle? Well, again, or that battery operated vehicle, it would be 20 divided by 100. Your output energy is 20 joules. The input energy would be 100 joules. 20 divided by 100 times 100, 20 divided by 100 times 100 is going to give me 20%. So that's calculation of efficiency. Pretty straightforward. And this formula, right at the very beginning of your data booklet, it's on the top of page 1. This would be sort of one of the mathematical sections of this unit will be how to calculate efficiency. Let's do a couple of examples. Here's a couple of examples on the notes here. I won't write it necessarily on the board. I will give you one extra one just for our own purposes here right now. But here's an example. If a device is 52% efficient, and the total useful energy output was 235 joules, what's the input energy? So one more time, if you haven't got the notes in front of you, if the device is 52% efficient, has a total useful energy output of 235 joules, what's the input energy? Pause me if you need to. I'm going to give you the answer here in about 2 seconds, show you how I calculate it. Here we go. Okay, so I use my equation. I've got useful output energy on the top. I got my total input energy on the bottom. In this case, it's all going to be in joules, times it by 100. Well, I know I've got 52, so it's going to be 52 equals 100. And I'm given the output energy, which was 235 joules. And I'm going to solve for x. So that's basically what I want to do. I want to solve for x. And in this case, my x is going to be 452 joules rounded to the closest single, I guess, to the closest integer, not to decimal point. So that's basically one right there. What's the energy that's going to be lost to the surroundings? So what's the energy that we're going to lose in this system? Well, it's going to be whatever, if this is my total input energy, and that's my useful output energy, then my lost energy is going to be the remainder. So remember, energy cannot be created or destroyed; it can only be transferred. And the transfer of energy is never 100% efficient. So in this case, the 100% efficiency would be the lost or the useless output energy. So in this case, I would simply take my 452, subtract my 235. That would give me wasted output energy now of 217, as you can see down here on the slide. So that's basically how you calculate. Remember, your useful and your useless output energy, if you add those two together, in theory should equal the input energy, because remember, you cannot create or destroy energy. It can only be transferred. So in this case, that useless output energy could be in the form of heat or noise, things that are not useful to the actual output of the device. An example I could say would be like a blow dryer. Blow dryer is going to be producing heat. That's the useful output energy of a blow dryer. The useless output energy of the blow dryer is the noise it makes. That's not something that's useful. That's just wasted energy. That's part of the fact that a blow dryer is not 100% efficient. Some of that energy is being transferred out as noise. So some of it gets wasted. And again, how efficient we can make the blow dryer. Again, in fact, a quieter blow dryer in theory should be more energy efficient. Be interesting to see if you have a blow dryer at home, see if you have a noisier or a less noisy one. If you have a new or an old one, see if the old ones are noisier than the new blow dryers in your house. How do we improve efficiency? Well, there's a lot of ways we can improve efficiency. Lots of ways we can do it. Hey, let's replace some light bulbs in our house. Most people have already been doing this over the last several years. You replace those old incandescent light bulbs with LEDs. They use way less energy, and we're not needing as much energy to actually light our homes, which is huge. How about more efficient vehicles, hybrid vehicles, electric vehicles? I know some of them are more expensive, but that is hopefully something that's going to be turning the corner here in the next few years, is that we're going to have more electrical vehicles, more hybrid vehicles, which are going to be more energy efficient, less use of fossil fuels to power them. What about making industry more efficient? There's a lot of industries in Canada that are actually reducing their energy demand, but also increasing their output. An example of this would be the Canadian mining industry. From 1990 to 2002, the Canadian mining industry actually decreased its energy usage by 12%, but actually increased its output of goods by 11%. So that's a positive sign that there are industries in Canada that are beginning to become more efficient with the use of energy and able to produce more goods with less energy input. So that's going to make our country less energy intensive, or our economy less energy intensive. Here's a question for you. What's more energy efficient, if we use hair dryer or hand dryers, or if we use paper towels in let's say a restaurant or at the school? Which is more energy efficient? Might surprise you, the fact that hand dryers are significantly, well, that shouldn't surprise you, I guess. Hand dryers are more energy efficient than using paper towel. And the reason why is because you don't have to produce a paper towel. You're reducing your emissions of greenhouse gases. Even though the hand dryers require energy, you're going to use less energy for the hand dryer to dry your hands than actually it takes to make the paper towel that you use to dry your hands. So that's why if you ever have the choice between like an air dryer or paper towel, if you want to be energy efficient, use the air dryer. You are doing you're doing the planet good by doing that, because you are reducing your per capita energy consumption. One last thing, we should maybe spend a little less time on the internet. This is not something that we normally think about when we think about energy consumption, but the internet is a massive user of energy. And we don't really think about this because it's at our fingertips every day, but it is a massive, massive power monger. It uses tons of power. And the reason why, I'm going to get you to watch. This is a great little video. This video talks about why the internet is such a monster user of energy, and can we make the internet more energy efficient? This is something that we're going to need to deal with as more and more streaming services and the more we use bandwidth, the more energy we are in fact using. Watch this video. Great little take on why you should always think about when you're on the internet, because you are actually using energy, not just the energy of your computer, but to actually make the internet go round and round. It requires a lot of energy to make that happen. It doesn't something not a lot of people think about when you're surfing the web. One other thing we can do is increase the efficiency of our electrical power plants, the sources of our electrical generation around the world. Generally speaking, power plants cannot produce more electrical energy at peak hours. Normally, most electrical power plants will generate a consistent amount of energy all day long, which is kind of wasteful, because at certain times of the day, the energy usage is not as high as at other times of the day. So could we make it so that we could alter the amount of energy that's being produced at, let's say, off-peak hours to make these electrical power plants more efficient? And there is a way we can do this. There are two main types of electrical power plants that are running, in any given area around the world. You have what are called either base load or peaking power plants. And what's the difference between the two, and which one is more energy efficient? Well, the base load power plants are basically providing continuous supplies of minimal demand electricity throughout the day. And these can be either hydro, nuclear, wind, or coal powered. So they're producing a minimal amount of electricity all day long. Then, on top of that, you would have a second power plant that would then kick in. So to make the system more efficient, you would have two power plants. You'd have your base load power plant sort of running at minimal electrical output, which would be good for off-peak hours. Then you would kick in a second form of an electrical power plant, which is called a peaking power plant, which would kick in at peak hours. And this only would kick in during peak demand. They would produce this extra electricity at a higher cost and lower efficiency. However, these plants will command they're gonna be more expensive to run, but generally they're only going to be used for short periods of time during peak hours when it was necessary for them to kick in. So you're going to give up a little bit of efficiency, but if you're only running these plants for, let's say, 2 or 3 hours of the day, as opposed to a standard power plant that runs higher amounts of energy and is maybe a little bit more efficient than a peak power plant, but is way less efficient than, let's say, a base load power plant. If your base load power plants are running 24/7, then you are going to hopefully create a system where the energy creation is going to be way more efficient, because you're creating a much more energy efficient way of electrical generation, and you're using potentially renewable resources for the base load power plant, and then you're only going to have to use a little bit of fossil fuel, or you could also have solar powered or natural gas in there to basically run those peaking power plants at those peak hours. To put it in perspective, what Alberta does, Alberta right now, 41% of electricity is generated from coal, 40% is from natural gas, and the remaining 19% comes from a combination of either water, wind, biomass, or waste heat from burning coal. That would be a technique that's used by the Genesee power plant, which is in the diagram right down there. on the shores of Wabamun Lake, which is a major power plant in the Edmonton area that produces a lot of the energy that the Edmonton area utilizes. So that's, a lot of our energy consumption, or sorry, a lot of our energy generation, electrical energy generation, is in the form of burning fossil fuels, either coal or natural gas, about 82% in Alberta. So Alberta's got a ways to go where it comes, where can we be more efficient using more renewable resources? And I'll be running through some of these renewable resources in this unit to look at potential options. I mean, are we going to be able to use hydroelectric dams to do it? Well, probably not. We don't have enough, really high flowing rivers. We do, and there are some. I mean, but again, a lot of them are in national parks, so there becomes that whole battle of where do you put a dam up. But if you've driven, let's say, past Nordegg toward David Thompson country, there is Abraham Lake, which is actually a dammed portion of the North Saskatchewan River, which does generate some hydroelectricity from that dam. So we do have some hydroelectricity in the province, just it's not in areas around here. We would have to go further west to areas where the rivers are faster flowing, and there's all the whole, what are we doing to the ecology of these areas in the Rocky Mountains if we start damming off these rivers? But again, we'll have more discussions about that later in the unit. That's our first conversation for Unit D. Hope that worked out well for you. Here's your homework. I want you to complete practice questions 6 and 7 and 9 and 10 on pages 473 to 477. And I'd like you to complete questions 2 to 8 and 10 to 12 on pages 479 and 480 of the textbook. That's our conversation today for 1.1. Won't you join me next time when I'm going to basically propose to you that pretty much almost every energy source we produce on this planet is technically solar in origin. Yeah, even fossil fuels, believe it or not. But is it really solar? Yeah, we'll find out. Anyways, that'll be my topic for 1.2, solar fuel from the past. Until then, folks, thanks for tuning in and have yourselves a great day.